Hello, am I audible? Hello. Let's wait till 6:10 and then we shall start. I'm waiting for a few more people to join. Connect me. So, just um, uh, let's wait for 5 more minutes and then we shall start with assignment solving and all. Let's wait for some few more people to join. I have to keep a track of attendance as well. So, hello everyone. Let's wait for 5 more minutes. Please don't leave. Hi Venkat, how are you? Am I audible, right? Okay. Let's wait for 3 more minutes. Okay. Are you guys facing any problem in the course? Is like everything going fine, or are you stuck somewhere? Do you want me to teach some specific topics or coding? After sixth week starts getting tough actually. Before that, it's fine. So today we will be discussing. Let me write it down here. Week 2 solutions of. Yes, I can hear you. Okay. Page rank, right? Okay, I'll explain it. Just a second. Week 3, 2023, 2025, 2. This we will be solving. Week 2023. I cannot edit it, right? 24. This will be solving today, but before that we shall solve page rank. So since this is your specific doubt, so I'll just handle it directly. Just a second, I need to share my screen first of all. I need to allow share entire screen. Then I need to open my iPad. Is this visible? Is this screen visible? Okay. So what is basically page rank? I will just give you an intuition first, then let's go to the maths and everything, and it's okay like to feel overwhelmed initially. So first construct a directed graph. Somebody just keep your mic on unmute and say yes and no, because if it gets disconnected now I won't be able to know because my screen is completely white right now. Okay, so this is something like a directed graph. Something like this. This is visible, right? Okay, just speak fast because if I press my space bar now, I have to share again. Oh, this can also work. 8012. Let me see. Oh, the screen is visible, right? This writing is visible, right? I'm writing something. Not visible. Now? It's visible right now? Hello? Okay. So, page rank, what does it tell? Page rank basically tells how popular a node is based on number of incoming edges. Okay, this means that how big of a hub, sorry, how big of an authority is it is. Okay. So assume there's a website which contains every paper of the world. So assume that archive.org has every paper in the world, and now every paper, every citation just points to this archive.com, archive.org. Okay, so the page rank of this, so if anybody tries searching any paper, what Google will do, Google will basically search that paper inside archive.org first, because if it searches somewhere else, it will be difficult to find, because every other paper gets is basically citing archive.org. So it knows that archive.org has a lot of papers, okay, and it's referenced. They are referenced in all of the other papers as well, okay. Now assume there's a website, okay, which is referred by archive.org, okay. So assume these papers call archive.org, and then this archive.org basically refers to Scholar, Google Scholar, okay. So this also means that the website which is being referred by everyone refers to some other website. This means that this website, so assume this is Google Scholar, this is archive. Got it till now? Say yes or no. Okay, so this is Google Scholar, this is archive.org. So what does it tell about it? It tells basically that now the PageRank was proposed by Google actually. So I'm referring this whole setup as a Google search thing, okay. So now assume I'm searching something on Google Scholar, on Google, it shows archive.org. The second best thing it will show me is the second best results will be shown from Google Scholar, not from some other website, because there's only one edge that is going outwards from the most referred to website. Okay, so this is like something about what we call PageRank. So PageRank of archive is basically number of incoming edges. I'm just writing it here, like hypothetically. I would not say, I'm writing it heuristically what it should mean, like, and as rough estimate, number of incoming edges plus some weight, like say like this is 1 multiplied by 1 time, now this is multiplied by 1 by 2 times number of incoming edges on nodes with incoming edges, on nodes connected to incoming edges, okay. And this goes on like this, plus 1 by 4 times. So what I'm saying is, so PageRank of archive.org is basically total number of incoming edges, 1 2 3 4 5 plus there are some nodes which have incoming edges. So 5 has, sorry, I need to write it like this, okay. So I'll write 1 by 2 times 5 has 1 incoming edge, okay. Then 4 has 1 incoming edge, okay, plus then the neighbors of these as well, like, okay. So I go to 5 as well, I go to, like, I make it 1 by 4, I go to 5, the incoming edge coming towards 5, okay. So this was incoming edge coming towards 5, I go to this edge, this node, and see how many edges are coming to it. So 1 edge is coming towards it, okay. Similarly I go to, sorry, 4 has 2 incoming edges, basically 4 has 2 incoming edges. I go to these nodes and they don't have any incoming edges, these nodes, okay. So this will be the proper PageRank. This will be 3 by 2 plus 1 by 4, 5 plus 1.5 plus 0.25, that is 6.75. This is the PageRank for archive.org. Okay, this is like weighted PageRank something. I'm just giving a rough estimate. I'm not computing by a formula or something. You can compute easily by a formula. It's like not very difficult. Audible, right? Okay. Now I'm asking you to compute PageRank of Google Scholar. So if I just take PageRank of Google Scholar, there's only one edge coming, correct? From archive.org, just one edge is coming. Okay, that's fine. PageRank should be 1, but it has a very influential node coming towards it. So I write 1 by 2. This node has 1, 2, 3, 4, 5 edges coming towards it. Okay, plus again we make 1 by 4 and we repeat the same thing 1 by 4. So for 1 by 4 we basically take from here. Why from here? Because 1 by 4 is 1 by 4, 1 plus 2, then 1 by 8, 1. We do this because like the weight is like geometric progression going towards 1 by infinity something. And this is like again the neighbors of, these are the neighbors of the node connected to Google Scholar. So it becomes 1 plus 2.5 plus 0.75 plus 0.125. Okay, it becomes 3 point something something something. It becomes 4 point something something something. Now this means that page rank 4 and page rank 6, they are like quite high comparatively. This means that these two nodes are most influential nodes in this whole graph. Okay, so this basically tells one thing about it. This basically tells that if I don't if this strong node is not connected to Google Scholar, some weak node is connected, the page rank will be around 1 point something something something. Now due to this strong node being connected, this page rank becomes 4 point something something something. Okay, got it? This is very basic. I will tell you some more things as well. Okay, I'm sharing my screen, that so I'll tell you formula. I'll explain you the formula as well. Page rank formula. So this should be visible, right? This Wikipedia is visible. See, it's visible, right? Okay. So see what I explained. B is a very popular node here. A lot of edges are coming towards it. So it has page rank of 38.4%. C is the only node connected to, C is like connected to only B. But since B is popular, so popularity is getting transferred to C as well. Okay, so let me explain via formula. So see, it's also doing the similar thing. So you do page rank divided by some out degree something something. Okay. So see, this is the formula for page rank. Okay. So it basically tells, let me explain the formula. I won't be able to write here. I'm not sure like how to write here. So see, this tells basically page, I will explain this term later on. First, let me explain this term. So basically it tells page rank of PI, page rank of Google Scholar is equal to summation okay, of page rank of all the nodes which have incoming edge towards Google Scholar. Okay. So PI, P1 to PN are the nodes under consideration. Just a second. Yeah. PI, MPI is the set of pages that link to PI. Okay. So Google Scholar will be coming here. Google Scholar is PI. MPI is just archive.org. LPI is the number of outbound links. So how many edges are going outside from that? Okay, so if PJ on that node, so basically this is like some hard and fast formula, they have derived it, but it basically gives the similar type of results only, and is the total number of pages or number of nodes. Okay, so what you do is you define a damping factor here, D. Okay, this damping factor basically ensures that there's some weightage given to the number of neighbors and some weightage given to this term. So assume you take damping factor of 0.8. So what does 0.8 means? You multiply this by 0.8, and now assume there is a node PI which does not have any incoming edge. So assume this is the node. Okay, they don't have any incoming edges here, but they have 1.6% of page rank. How? Because of this term. So this is basically a random jumping term, just what we call where like if we subtract 0.8 out of this, so it will become 0.2 divided by total number of nodes. So you have to give page rank to each and every node initially, because if you don't give them, their page rank becomes 0 or infinity and they don't help anywhere. So you give them some small page rank, and then then we basically apply this formula here. Where's the formula? Okay, I think it should be easy to understand, right? Any more doubts? Do you have or does anybody have any more doubts? So, like, do you want me to solve any other question of page rank? Okay. Yeah. Okay. So let me do it for this one. Okay. Let me draw it up. Just a second. Let me draw it. I won't be able to show you because I'm not able to see this screen. So first let me draw it, then I will show you. See. So there's one more thing about page rank. You have to do it again and again, like multiple times. I'll tell you why. 1, 2, 3, 4, 5. I may miss out on some edges. Just bear with me. There are a lot of edges. 1, 2, 3. 1, 2, 3, 4. Okay. 1, 2, 4, 4, 4. One more edge towards this side. 1, 2, 3, 1, 2, 3. Now it's done. Okay, let me write down the formula as well. Just in case, page rank of node pi is equals to 1 minus d by n plus d summation of pj belonging to m of pi, page rank of pj divided by l of pj. L is number of outbound links on page pj minus total number of nodes. Okay, fine. This is visible, right? Okay. Now what we are gonna do is, so we start, I forgot to label. We see A, B, C, D, E, F, G, H, J, K, L. So let's compute page rank of these nodes. 1, 2. Those nodes the nodes which don't have any edges coming towards them. This one as well. No, this one, sorry. This one has an edge coming towards it. This one has an edge. So page rank of all the nodes G, H, J, K, L is basically, the damping factor is 0.85. It's generally set to 0.85. 1 minus 0.85 divided by total number of nodes 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that is 0.15 by 11. Okay, so what is 0.15 by 11? Just let me compute. It gets somewhere around 0.0136. So that is 1.36%. It should be like this. Okay, so as you can see here, 1.6 or 1.36. I don't know like how they computed. They might have taken 0.2 or something. 0.2 divided by 11. Yeah, 0.2 if you take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So you see, you get similar ratio 1.6. All for all, everything is the same. GHJKL, everything is the same. Now it should be visible. Visible, right? Okay. Next, you to take some other node. So, like, let's take this node. Because it has an incoming edge, so let's not take this node for now. Let's take those nodes. So the problem here you can see is if I take E, I'm explaining the problem first, then I'll tell you the solution. I have incoming nodes, these 1, 2, 3, 4, 5. And then there's this node. For this, I don't know page rank. Okay, for now I don't know. So let's compute again. Let's compute page rank for this. So page rank of F is 1 minus 0.5. So let's write it down. 0.016, just whatever they have written, 136 plus 0.85, then summation. How many incoming edges are here? Just one, E. Okay, so we write page rank of E divided by edges going from E. Number of edges going from E, it should be like this here. So then what will be it? It will be 0.0136 plus 0.85. It becomes a nested thing. Then you write page rank of, so let me write it down. There are only 2 edges going out from it. Let me write it down just here, 2. Now how do we compute page rank of E? It becomes a nested thing, see. 0.0136 plus 0.85. Page rank of E has basically the number of outgoing edges are 1, 2, 3. There are 3 edges going outside. So it takes page rank of B plus page rank of D plus page rank of F. See, B has 1 outgoing edge, D has 1 outgoing edge, and F has 1 outgoing edge, or 2 outgoing edges, sorry. Okay. E has 3 outgoing edges. Okay. Hello? Yes. Okay, no problem. So this let me do it again. Okay, so for F, then you take P of B as well. Okay, and B has 1 outgoing edge. So to compute P of F, you have to compute P of B. To compute P of B, let me write it down. So it becomes a very complicated thing. That's why generally when the questions are given to solve manually, they are very easy questions because it becomes a nested problem. And then you have to do it iteratively. For after first cycle, what nodes get what value. I'm just writing it down for you. 0.0136 plus 0.85. Now B has 1, 2, 3, 4, 5, 6. No, this won't be P of B. Just incoming edges are taken. Sorry, just incoming edges are taken. 1, 2, 3, 4, 5, 6, 7. 7 nodes. So P of D by 2 outgoing edges, plus P of G, that is 0.0136, plus P of H, that is again 0.0136. Similarly, we keep on doing. And since these nodes have 1 outgoing edge as well, we divide it by 1, doesn't matter. Okay. Then we take J, then we take K, then we take L. Okay. So this is how we compute. So coming here, we don't have P of D and P of G. So we compute them again. P of G we have. Just P of D and P of C. Okay, so you see P of C and P of D are not computed for P of G, But if you compute P of C, again you have to compute P of B by how many outgoing edges? 1. Okay. So basically, see, this is nested. This is linked to each other. Okay. So what is the problem here? You can see. The problem here is whenever you are given question, you will be given an initial value of page rank. Okay. You will be given an initial value in question paper, in whatever question papers we will do, or in quizzes, in assignments, whatever you have, you will be given an initial page rank value. You have to use it to solve it. Okay, so that strategy, the common strategy is to solve it generally from nodes with no outgoing edges to nodes with high outgoing edges. Okay, I'm not writing there, I'm just writing no outgoing and high outgoing. Okay, so I'm telling you. So this is how you do it. So just let me show you one thing here. Because there's no easy way to do page rank if the initial values are not given. I think page rank comes in week 4. Not one question should be there in week 4. I don't know. Yeah. Okay. So alpha, like I think the deadline is over. Yeah. So see, you are given initial determine first iterations. You are given initial values of page rank. Okay. So the rank at 0 is given to you. You have to find rank at 1. Okay. And give using these things. So you take nodes with, you take any node and you start computing. And just you have to just do one iteration. Okay, just one iteration. You will be getting answers like this. I'm not solving it. It's very tedious. And it requires calculator as well. Okay, so yeah, this is this. This is like everything about page rank. I'm not going into detail of solving it. You start solving it. If you have any doubts, you can discuss with me. Where did you go wrong? I can like tell you. Okay. Try solving it. If you're not able to solve, just join next session and I'll just show me where you are facing issues. I will help you from that step onwards. Okay. Yeah, so this is about page rank, and now let's go and solve assignments. Just a second. Let's solve week 3 and week 3 assignment first. Week 3 of this year. Just a second, hold on. Hello? Sir. मैपटेक्स है सर. मैं सर आपको ना भेजता हूँ. मैं NPTEL ले रहा था, अभी मैं भेजता हूँ आपको 5-10 मिनट में भेजता हूँ. Hello, am I audible? Just a second. I need to rejoin. Hello. Okay, sorry about that. My earphones got connected to mobile. Am I audible? Right? Okay. So yeah, I was doing assignments. What is okay? First of all, tell me, did you face any issues in week 3 or not? If you have faced any issues, let me know. I'll just tell you explicitly those questions first, and we'll go from start to end. No issues. I'm assuming there are no issues. Okay. Which of the following is a necessary condition for a network to exhibit small world property? So small world properties basically tell the size of network is exponentially related to. Let me just present my screen. I cannot. Wait a second. Wait a second. Let me join on this one as well. Mute. If you hear any echoes, just let me know. I don't. Are you hearing any echoes? No echoes, right? So two screens should be visible to you. I hope so. Just let me know if they are not visible. Two screens are visible. Hello, guys. Two screens should be visible, okay? Because on one screen I will show question paper. Okay, so see. So there's a one formula, I'll just tell you simply. So average path length of the network is basically proportional to log of size of network. Okay, size basically comes from the longest, shortest, and whatever we say, like diameter and everything. Okay, and average path length is you compute path length between all the nodes, between all combinations of A and B. You take average of it. Okay, this becomes the average path length is proportional to this thing. Okay, this tells you that networks exhibit small world property. Okay, so how does it matter actually? Can anyone tell me how does it matter? How does it hold relevant? Just say yes, no, I'll explain it. Anyways. Okay, so let me explain. What is the, like I assume this is a small world network. See, just two nodes, very small network. Okay, what is the size of network? Just one edge, right? Is proportional to log of 1. Okay, that's why we don't make a network with one edge, just one edge. Now it has 4 edges. We take log 2 is proportional to log of 2 base 4. No. But what is the diameter? Diameter of this network is 1 A to B 2 log 2 2. See, 1 is proportional to 1. Okay, so this is one very basic example, and I'm going to tell you how is this relevant. So small world property tells that the network, like we 6 people are sitting, we 4 or 5 people are sitting, 3 and 3, whatever weird combination. Okay, so now we 4 or 5 people can interact with each other. And it's not like you cannot, like 2 3 B01 cannot interact with B24. So this is a very small network. So the idea of small network comes from completeness of a graph. Completeness of a network. Completeness means all nodes connected to all nodes. Complete graph. Okay, got it? Hello. Okay, why does it matter? See, so as you might take this graph here. Okay, so average path length from A to B, C, D. You can go to any node in just one hop. Okay, this is the basic necessity of a network for to exhibit a small world property. Okay, and what is the diameter? So diameter basically of this thing becomes from A to B is in 2 hops, like shortest one. And as you might take one node here as well, I connect it to E. Okay, so the diameter of this network becomes 2. So again log of 2 you take, it becomes proportional to 1. Okay, so this network exhibits small world property. This as well because it's very small. So a small world property gives a basic intuition. So see, size is a very big term. So we compute log over it to make it uniform with a normal scale. Okay, and then we compute average path length. So average path length is basically the path length between all the possible nodes, and take its average. So this what gives a basic intuition to us that the average path length and the maximum possible path length, they are equal. Means that network is more or less connected in such a way that it's very easy to transfer information from one person to another person. Okay, so real world networks exhibit those properties. I would be connected to anyone on Facebook who is not my friend. Okay, got it? So this is where from where this small world property comes into picture. It's again a very basic question. Adversarial network, the probability distribution is given by Poisson ratio. If you read, go through the chapter, you will find it. In Watts-Stugart's model, increasing the rewarding probability from 0 to 1. So if you increase the rewarding probability from 0 to 1, it rewires everything. Okay, so it gives like the average path length decreases because now the path length between the nodes which are far. Okay, and if I increase rewarding probability, so this is getting connected to this to 1. If I increase it to 1, it becomes basically fully connected. If I increase it to 1, if I don't increase it to 1, it becomes a single cycle type of thing. Okay, so if you're going from 0 to 1, you are like decreasing distance or average path length, and obviously you preserve high clustering coefficient, which is the property of it, because all the nodes are connected in a cluster as only. Okay, any doubts? If you have any doubts, just let me know. Okay. The preferential attachment mechanism in Barabasi-Albert model implies that link nodes basically high degree nodes get high probability that new nodes will be connected to them. I'm writing it, but like it's speaking coming out of mouth, and you can understand it. So new nodes will be joined based on the current degree. Virat Kohli will get more followers than me at time t plus k. Okay, that's because he currently has a very high degree. So this is what Barabasi-Albert model tells you. For a random network, the average, the critical average degree at which the giant component emerges is approximately close to 1. Okay, it's given in the book. I cannot solve it today. I don't have the book today. I will have shown you. Next class I can show you this as well. There's a very nice proof for this. Okay, just remind me, Venkat, you attend all the classes, I think. Just remind me in next class, please, that I have to show proof of this. Okay, I don't have the book. If I start speaking, you won't be able to understand a lot of things. So let's just wait. Let's just wait till 1 week. I'll explain it. Very nice formulation of proof behind this. Okay. So this is again like NC3 P3. This is based on which should we call NC3 P3? What do we call it? Permutation combination. Since this follows Poisson distribution. The Poisson distribution is basically related to. Let me show you. Poisson distribution. Okay, let me show you how its formula is related. Okay. That formula comes from Bernoulli, I think. Aldous Rennie. Okay, see, this is the formula. So this is basically n minus 1 ck, pk, 1 minus p, n minus 1 k. So this comes from binomial properties of binomial distribution. Okay, and if you take n tends to infinity, this distribution becomes Poisson, and this becomes the formula. Go through it. This is a very interesting, what do we call, understanding of a Aldous-Rennie model. Okay, so we write it similarly. We write NC3 because we are considering 3 cycles. Okay, and we take p to the power 3. Which network model best produces heavy tail distributions in real world? Obviously, out of this, Aldous-Rennie basically produces flat networks, Schwarz circular networks. Barabasi-Albert only produces heavy tailed, something like this. Very low number of nodes with high degree. Okay, say 20 nodes with high degree and around say 50,000 nodes with low degree. Okay, for a graph of a size 1 million something. Just a second. I need to pin it as well for myself. Okay, any doubts till now? Venkat, Niruda. Okay. I mean, these questions are coming directly from the theory, so there's nothing to explain for me as well. In configuration model, the connectivity of graph is largely determined by which property? So basically this configuration model, let me explain you, because I think this was not taught, what should I say? exactly. I think this was not taught at all. Okay, so configuration model is the family of random graph model which comes from Adosreni model. They preserve the degree of each vertex as predefined property. So degree won't change. Okay, just a second. Modular to construct networks with arbitrary degrees, making reference model, particularly in social, biological, technological domain. Okay. Configuration models can be specified for simple graphs, multi-edge graph, loopy graphs, directed graph, undirected graphs. Okay. So, first of all, the answer is second moment of degree distribution. That is fine. Let me tell you how it comes to that. See, see, see this thing. Okay. Sorry. Just a second. Okay. So what is connectivity? Connectivity basically comes to, am I audible, right? I'm audible? Okay. So see, connectivity comes from the giant component. If there is a giant component which exists in the graph, it means network is connected. So if the network is strongly connected, it means that the giant component is the graph itself. Okay. So as you can see here, the connectivity depends on the first momentum and second momentum. This thing. First momentum and second momentum degree distribution. K square minus 2k should be equal to, or so it should be greater than 0. Okay, so this is why it depends on this thing. The assortativity coefficient of network measures, what does it measure? Correlation between degrees of nodes. Okay, so I think this was also not taught. Assortativity coefficient. So assortativity coefficient comes from correlation coefficient. See, you can see this image. Okay, so basically take all the combinations of nodes 1 2 1 4 1 5 1 and 3 are not connected, so this is not this image is visible, right? Let me open this image. This image is visible. So we take 1 2 1 4 1 5 2 4 3 4 3 5. Degree of x, degree of y, we write it like this. Average, what is average of x? Average of x, okay. Average of x 2.5, average of y is 2.5. So you subtract x minus average of x, you get these values. Y minus average of y, you get these values. You multiply it, you get these values. And this is how you compute assortativity index. Okay. So basically this is coming from correlation between degree of connected nodes. Correlation coefficient, okay. So this is how assortativity index is computed. Correct? Any doubts? No doubts, right? For scale-free network with degree coefficient, degree exponent gamma, I just wrote it, e to the power gamma. Between 2 and 3, the statement is true. Obviously, random node failures leave giant component intact. Okay, so this is also coming from theory only. I'm not teaching anything hi-fi here. Giant component largely intact. Random node failures. Yeah, so node failures basically are coming from the node gets deleted, poisoned, or destroyed, but the giant components remain intact because the gamma value is between 2 and 3. Okay, so you remember this thing. This is a property. The higher the value of gamma, this property starts holding true. If the value is greater than 1, it starts holding true. Okay, so this is for week 3. Let's quickly visit week 4. I won't. Do you have any doubts in week 4? Not numerical doubts, normal doubts. Like theoretical doubts if you have. Like numerical doubts if you have, I can solve it, but that will be for next class because week 4 is not supposed to be taught in this class. If you have doubts in question 5, I will solve it in next class. I will solve this question in detail in next class. If you have doubts in question 4, it's very easy. It's like damping factor. Alpha is damping factor. It damps how much weight we want from the out degree, or like how much weight we want from the graph itself, the number of nodes. Okay. The node with lowest out degree is always most prestigious. False. The node with highest in degree is the most prestigious node. Highest in degree is the most prestigious node. Time homogeneous random walks are where the transition probabilities remain constant over time. Okay, so you take this graph, you start computing T1, T2, T3, all the iterations, and if these probabilities start becoming same, so it becomes a random graph, which is not property of path sim. This thing, triangle property is not satisfied by path sim, and rest are all numerical questions. So you try solving them. If you're not able to solve, now we'll solve it in next class and discuss this thing and remaining things as well. Okay, and Venkat, please remind me to do the proof of large strong connected component whose average thing something becomes 1. Average path length becomes 1. Okay. Any more doubts? Any more doubts, guys? Okay, then see you in next class. Bye bye. Take care. Have an awesome weekend. Okay, I'm leaving. Thanks.